In today's lesson, we are giving our Arduino real power, not just to reading sensors or blinking LEDs, but actually controlling a motor safety, the same way real control systems work in the world outside your desk. You are going to learn how to use a relay, how to use a transistor, and why these two tiny devices are the reason a small 5-volt board can command much bigger things. Welcome to lesson 18 of our 24-part series called Arduino for Beginners. Let's start by taking a closer look at the relay module. A relay is an electrically controlled switch. It allows a low-power circuit like Arduino to control another circuit that may use a higher current or a different voltage. Inside the relay, there is an electromagnetic coil. When current flows through the coil, it creates a magnetic field. That magnetic field physically pulls a small internal metal contact, which either opens or closes a circuit. So even though we control it electronically, the switching itself is mechanical. This is extremely useful because Arduino works with small signals. Its digital pins operate at 5 volts and can safely provide only a limited amount of current. Motors, lamps, pumps, and many other devices need much more than that. If we tried to power those directly from an Arduino pin, we could permanently damage the board. The relay acts as a safe middleman between the small circuit and the more demanding circuit. The relay module we are using today has two sides: the control side, which connects to Arduino, and the switching side, which connects to the device we want to control. On the control side, there are 3 pins: signal, VCC, and GND power the electrons on the relay module and the coil inside the relay. This should be connected to the 5-volt and ground pins of Arduino. The signal pin is connected to one of Arduino's digital pins. When Arduino sends a high signal, the board activates the relay coil. When it sends a low signal, the coil is deactivated. On the switching side, we have the terminals that behave like a regular switch. Think of this as the 2 wires of a cable that we are going to open and close electronically. The terminal labeled CON receives the positive wire coming from the power source of the device. Then we have 2 possible outputs, NO and NC. NO is the normally open contact. That means that when the relay is off, the path is open and no current flows. When the relay is activated, the internal contact closes. The current can flow from CON to NO, turning the device on. NC is the normally closed contact. Here, the logic is reversed. When the relay is off, current flows. When the relay turns on, this path opens and current stops. So by choosing between NO and NC, we decide whether our device should be on when the relay is activated or when it is deactivated. It may sound a bit abstracted now, but once we wire the project, this will make perfect sense. Before we start building, I want to thank DF Robot for sponsoring this series. DF Robot provides open source hardware for makers, students, and engineers. And for this course, they stand behind Plus Arduino Code Kit. It includes sensors, modules, and accessories that make it much easier to follow these lessons and build real projects step by step. If you want to build along with this series, you can find the link to the kit in the description below. Thank you DF Robot for supporting this course and helping make STEAM education more accessible for everyone. Now let's get back to the video. If you remember the previous lesson, we built a system that measures temperature using the LM35 sensor and shows the value on an I2C LCD. Today, we are upgrading the project. We are going to add a motor that acts like a fan. When the temperature goes above a certain threshold, the fan will turn on. When it drops below the threshold, the fan will turn off. This is a simple prototype of a thermostat. For this project, we will need Arduino Uno, input-output expansion shield, LM35 temperature sensor, I2C LCD module, relay module, push-button module, a small motor, a diode, I choose one called H23FR207G, a battery, and a few jumper wires. Start by placing the input-output expansion shield on top of the Arduino. Connect the LM35 sensor to analog pin A3. Connect the push button to digital pin 2, then attach the LED module. SCL to A5, SGA to A4, VCC to VCC, and GND to ground. Now we add the relay. Connect the VCC pin of the relay module to 5 volts on Arduino and GND to ground. Then connect the signal pin of the relay to digital pin 3. Next comes the motor circuit. We will power the motor using an external battery. Take the positive wire from the battery and connect it to the COM terminal of the relay. Then connect NO, normally open, to the positive wire of the motor. The negative wire of the motor goes back to the negative terminal of the battery. There is one very important component we must add here, the flyback diode. We use the diode H23FR207G. Motors are inductive devices, and when they turn off, they generate a high voltage spike that can damage transistors, relays, and other electronics. The flyback diode gives the spike a safe path. Place the diode directly across the motor terminals. The distributed side of the diode goes to the motor's positive terminal, and the other side goes to the motor's negative terminal. Under normal operation, the diode does nothing. When the motor turns off and the voltage tries to spike, the diode conducts and protects the circuit. If you need additional help, check the schematics on the screen right now. After finishing the wiring, go to the GitHub repository for this series, the link is in the description below. Open the folder for lesson 18, download the file thermostat prototype and open it in the Arduino IDE. Before uploading the sketch, make sure the dfrobot grb LCD 1602 library is installed. Once the library is ready, upload the code and watch your board. At first glance, this project looks similar to the one we built in the previous lesson. When the system starts, the LCD shows the temperature in Celsius. Pressing the push button switches the display to Fahrenheit, and pressing again changes it back to Celsius. Now, here is the interesting part. I will bring a lighter close to the LM35 sensor to raise its temperature. You can see the value increasing on the LCD in real time. Once the temperature passes a defined threshold, the fan starts spinning. After some time, when the temperature drops again, the motor stops. Pretty cool, right? And now that you've seen the project working properly, let's go back to the sketch and understand how everything works behind the scenes. Most of the code is the same as in the previous lesson. We initialize the LCD, read the temperature from the LM35, and handle the button that switches between Celsius and Fahrenheit. The new part is the control logic for the relay. We define the temperature threshold, for example 50 degrees Celsius. Then inside the loop, after reading the temperature, we compare the measured value with that threshold. If the temperature is higher than the threshold, we set digital pin 3 to high. That sends a signal to the relay module, energizes the coil, and closes the path between COM and NO. The battery is now connected to the motor, and the fan starts spinning. If the temperature is below the threshold, we set pin 3 to low. The relay coil is deactivated, the internal contact opens, and the motor loses power. This is the key idea. Arduino is not powering the motor, it is only deciding whether the motor's own power source is connected or disconnected. Before I move on, think about this. What would happen if we use NC instead of NO? Well, if you know the answer, tell me in the comments below. Relays are very useful, but they have a limitation. They are mechanical devices. A small piece of metal physically moves inside them. That means they wear out over time. They make noise and they cannot switch extremely fast. If we need to switch something several times per second, it's way better to use a transistor. Transistors are also electrically connected switches, but they have no moving parts. They are made from semiconductor material. With a small signal at one terminal, we can control a larger current flowing between the other two. The transistor we use today is called BC547. We've already relied on it when we built the street line model on lesson 13, but that time I didn't explain to you in detail about how it works. The transistor has 3 pins: base, collector, and emitter. If the transistor is so-called NPN, a small positive signal into the base allows a larger current to flow from collector to emitter. But if the transistor is a PNP type, the base requires a negative signal to allow current to flow from emitter to the collector. You see? One is the opposite of the other. We had a lot of theory about transistors so far. Let's get our hands dirty and build another cool project. Now we will build the same thermostat idea, but this time using a transistor instead of a relay. Unfortunately, the transistor you use today is not powerful enough to work with motors, so instead we use a LED. In addition to the materials we used previously, you will need a breadboard, 2 resistors, 2K and 5K ohm, a transistor, I choose one called BC547, and a LED. Start by removing the relay connections. Place the BC547 transistor on the breadboard, then attach the LED, a 5K resistor on base, and the 2K resistor on the LED. After that, connect the positive coming from Arduino's 5V pin on the 2K resistor, and the negative wire goes to emitter. In the end, connect a jumper wire from digital port 3 to transistor's base through the 5K resistor. The rest of the circuit, including the sensor, LCD, and button, remains the same. Now, if the wiring sounds confusing, just follow the schematic that is appearing on your screen. Now that's ready, let's test the project. When pin 3 goes high, a small current flows into the base, the transistor turns on, and current can flow from the LED through the collector and the emitter to ground. Consequently, the LED lights up. When the pin goes low because temperature is below the threshold, the transistor turns off and the LED is deactivated. So when you should use a relay and when you should use a transistor? Relays are great when you need electrical isolation or when you are switching higher voltage or AC loads. They act like a physical switch and can handle different types of circuits safely. Transistors are better when you need speed, silent operation, and long life. They're ideal for DC loads like motors, LEDs, and other electronics, especially when switching happens very fast, or if you need to amplify signals. In some cases, transistors can control components that need lots of current, like motors, but that requires a special type of transistor called MOSFET. I won't cover it in this course, but it's something you should definitely learn about. As you may notice, both relays and transistors control high-power circuits using a small signal. The choice largely depends on the application. Before we finish, I have a quick announcement. I'm working on a masterclass about building drones using Arduino. You'll explore flight control, wireless communication, and power systems. If that sounds interesting, join the waiting list in the description so you'll be the first to know when this masterclass is available. That's it for today's lesson. Now you know how to use relays and transistors to let your Arduino control real device safely. These components will appear again and again in your projects, so mastering them is a big step forward. Subscribe if you haven't already so you won't miss the next lesson. And until that comes out, I recommend you watch the video appearing on your screen right now. Thanks for watching this tutorial and I'll see you in the next one.